this is about production function, and we will discuss this production function in different phases. This is part A, and in part A we will explain some theoretical concepts of production function. Actually, the technological relationship that describes the process whereby factors of productions are efficiently transformed into goods and services is called a production function. Mathematically, a production function uh, the functionality of the production function is the relationship between the capital labor and the land input, and so many other factors can be written as like that, where the quantity is the production output, and K stands for capital, L stands for labor, and M stands for land, and so many other factors can be added into this equation. But here I have only explained these three variables. The production function defines the maximum rate of output per unit of time obtainable from the given set of the productive units, and obviously some firms organize input inefficiently, thereby producing less than the maximum possible level of goods and services. In a competitive market environment, however, firms that do not adopt the most efficient, in other words, cost-effective production technology will not prosper and may, in fact, be forced to curtail operations as their market position is undermined by more aggressive competitors. In free market economies, there is a tendency of more efficient operations to drive less efficient firms out of an industry. For the sake of pedagogical, theoretical, and graphical convenience, let us assume that all productive inputs may be classified as either labor, capital goods. Labor is shown by L, and capital goods is shown by K. Equation may be therefore written as like that. In most cases, labor and capital may be substituted in varying degrees. As we will see, the precise manner in which these inputs are combined will depend on the relative rental price and marginal productivity of effective production. A firm that operates efficiently will choose that combination of productive inputs that minimizes the total cost of producing a given level of output. That would be, I think, a key statement where we can I would repeat that a firm that operates efficiently will choose that combination of productive input that maximizes the total cost of producing a given level of output. In our case, the productive inputs are labor and capital. Equivalently, a firm that operates efficiently will choose that combination of productive input that will maximize production subject to the given operating budget. So in both way, we want to maximize or optimize our production function, either to minimize the cost with the given level of output or to maximize the output with the given level of cost. It should be noted that the production function satisfies the technological relationship between inputs and output. It is an engineering concept devoid of any economic concept. The production function defines the maximum output obtainable from the particular combination of inputs. Input prices must be combined with the production function to determine which of the many possible combination of inputs is the most desirable given the firm's objectives, such as the profit maximization. Cobb-Douglas production function. Production function takes many forms, because if we are having some kind of a function, so mathematics obviously allow us to make so many kind of combinations and schemes over there. In fact, there is a unique production function associated with each and every production process. In practice, it may not be possible to precisely define the mathematical relationship between the output of a good or a service and a set of the productive input, because output and input combination may be in various of types. And in spite of all this, it is possible to approximate the firm's production function. Perhaps the most widely used functional form of the production process for the empirical and constructional purpose is the Cobb-Douglas production function. The appeal of the Cobb-Douglas production function stems from certain desirable mathematical properties. The general form of the Cobb-Douglas production function for the two inputs, in our case as capital and labor, may be written as like that. Q is equal to A, K raised to power alpha, and L raised to power beta. Here you can see, if I adjust these things, if where a alpha and beta are unknown parameters, and k and l represent the explanatory variable capital and labor respectively. It is further assumed that alpha and beta both are in between 0 and 1. uh, uh, there are more some information is needed to be explained. The Cobb-Douglas production function also illustrates the fundamental economic problem of constraint optimization. Although there are theoretically an infinite number of output level possible, the firm is typically subject to predetermine the operating budget that limits the amount of productive resources that can be acquired by a firm. Because of the restriction, an increase in the use of a factor of production requires the less of some other factors be employed. That is called a substitution. Because if you increase one input by reducing the other input, actually you are substituting one input for other. The degree of substitutability of inputs is important because it suggests the manager are able to alter the input mix required to produce a given level of output in response to the change in the input prices. Because if you are dealing with the labor and capital, you must know about the prices, and how the prices are changing of the land and of the labor and capital. So there must be a rate of substitution would be defined in prior, so the manager can fix their inputs easily. Law of diminishing marginal product, you know the term of the marginal product actually. And finally, the Cobb-Douglas production function exhibits a very important technological relationship, law of diminishing marginal production, also referred to the law of diminishing returns. This law sometimes refers to the to as the second fundamental law of the economics. It states that when at least one productive input is held fixed, while at least one other productive resources is increased, output will also increase, but the successive smaller increment. The law of diminishing marginal production is a short-run production function, because why it is short-run production function, or it is short-run production concept? Because one input is held fixed. When anywhere the input at least one input is remain fixed, so that tenor or that time duration would be called a short-run. Anyway, short-run production function is again defined in the production process. Economists distinguish between the short-run and long-run. The short-run production function refers to that period of time during which at least one factor of production is held constant. The law of diminishing marginal production is a short-run phenomena, and the long-run in production function occurs when all factor of production is variable. The average product of the labor, which is denoted by the AP of L, is simplified the total product per unit of labor used, and it's determined by the dividing the total output by labor, and the total amount of labor used. This relationship also can be defined like that, where average production of labor, as we said earlier, that it is simple ratio of total output divided by labor. And if our total output is determined, or it is given just as given here as a k raised to power alpha and beta, l raised to power beta, so all this function would be equally divided to the number of labor. There is another concept of the marginal product of the labor or any other factor. We can calculate the marginal product of labor, marginal product of capital, and here marginal product of labor is defined as as incremental change in the output associated with the incremental change in the amount of labor used. Mathematically, since the amount of capital is constant, this is equivalent to the first partial derivative of the production function with respect to labor. In our case, our production function here is given like Cobb-Douglas production function, a k raised to power alpha and l raised to power beta. So if this production function is being dealt with the derivative, partial derivative with respect to L, and applying the rule of derivatives where the power of labor, because we are calculating the marginal product of labor. So we take this power beta multiplied to a, the constant, the coefficient, and 1 is being subtracted from that power. So that becomes like that. You can see that the beta is being multiplied by the a, and 1 is being subtracted from the beta. This is the partial derivative of the function. So this term is can be called as the marginal product for labor. Similarly, we can calculate the marginal product for capital as well, where the same function is being again dealt for derivative, where the power of the capital alpha is similarly multiplied with the constant a alpha k, and 1 is being subtracted from the alpha minus 1 and L raised to power beta. So that term defines the marginal product for capital. Here you can see a simple example of calculating the average production and marginal production as a problem 1, where suppose we have the given following production function like that, the same Cobb-Douglas production function, but now here the constants are being defined, are calculated, where A is calculated as 100, k raised to power alpha is taken as 0.6, and b raised to power beta is zero point 0.4, L raised to power zero point 0.4. So that determines the marginal production of capital, marginal production of labor, when capital and labor is being defined by the two terms. So if we are given the information as here, capital is 25, labor is 100, so we can easily calculate the average production and as well as the marginal production for the both inputs. So marginal production would be for labor, marginal production for labor, as we said, that the function is being again dealt with the derivative of this function with respect to L, where 0.6 is being is for labor. So where the 0.4 is multiplied by the 100, here you can see 0.4 is multiplied by 100, and 1 is being subtracted from the 0.4. So by solving this, we can have this function 40 because 100 is being multiplied by 0.4, 40 k raised to power 0.6 and L raised to power minus 0.6. So that L raised to power of minus 0.6, that can be taken down under on in denominator. Here we can simplify this 0.6 same power for numerator and denominator. We can take it to one common parenthesis, and here we can put the values are given of capital and labor. Capital is given as 25, labor is given as 100, and by putting the values we can calculate the simple marginal output for labor. It means that at this stage where you are having 25 capital and labor 100, by adding one additional unit of labor, you will be having additional output as 17.4. And similarly, we can calculate the marginal production of capital as well. Again, that output combination, or that output function or production function is has been taken for derivative with respect to capital, and similar rule and principle has been applied, where the power of k, that is 0.6, which is being multiplied by 100, here you can see that, and 1 is being subtracted from the power, and the resultant function is like that, 60 k raised to power minus 0.4, L raised to power 0.4 again. And now here k is having a negative power, so that k is being taken to the denominator, you can see there, and by putting and by substituting the values given in the problem, we have such answer. This is the marginal production for labor. It means that at this situation, by additional unit of capital, additional 1 unit of capital, the total output will increase 63.4. So it's about information. Now the manager is responsible for the decision, he has to be having some information about the prices of labor and capital. He knows that after that combination of labor and capital, the output is being as 17.4 if one additional labor is being employed, and 63.4 unit of output will be increasing by adding of one extra unit of capital. So he can compare the prices with the output, and he can take the decision by which kind of change he can get the good and sufficient results. And here you can see that if capital is cheaper than the labor comparatively, so the capital must be hired in replace of capital, in place of labor. But where the labor is having very cheap than the capital, because 63.4 output is much higher than the 17.4, but the price of capital is too much high, that this output or this rise of output can be fade out by the adding additional unit of capital. So he must not employ the capital, but he should employ the labor as well. So these kind of decisions are up to the managerial or management psyche and attitude. How does these information can help the managers? Okay, now the next thing is isoquant, because when we are studying the production function, obviously we need to know about isoquant. Isoquant, the term has been derived from the Greek word iso means equal, and Latin word quantus mean quantity. Then the isoquant curves, obviously therefore also known as equal product curve. An isoquant curve is locus of points representing various combination of two inputs. Point to be noted, two inputs. Here in our example is capital and labor, yielding the same quantity of output. The factor of combinations are so formed that the substitution of one factor for the other leaves the output unaffected. It is done on the basis of the assumption that there is only two inputs, labor and capital in our case, and you can produce any commodity, let's say X here. The graph here depicts all the combination, let's say A and B, of labor and capital gives let's say 2000 units of output to a producer. Then the graph would be just like that. You can see this convexed curve is actually the isoquant line, and isoquant curve obviously is the locus of different combination. Here in this example we are taking just two combination, A and B. A mean L1 labor and K2 labor, and B point mean L2 labor and K1 labor. So with these combination, producer are producing same level of quantity. If he is using A combination or he is using B combination, in both combination he is maintaining his quantity 2000 unit unchanged. There are some characteristics of isoquant curves. So these characteristics are the slope downwards to the right. You can see that it is left to right downward slope because of the substitution. You can substitute your capital with labor or labor with capital. And this curves, obviously you are substituting these factors for each other in such a way that the output level is remaining unchanged. The second is it is convex to origin. You can see that it is not a straight line, it is a bit convex to the origin, and this is because of the diminishing marginal rate of technical substitution. Diminishing marginal rate of technical substitution for labor for capital. Marginal rate of technical substitution of labor for capital mean we are increasing number of labor by reducing on the other side by reducing the number of capital output. So isoquant curves is negatively sloped, and two isoquant curves do not intersect each other. Similarly, just like an indifference curve, and because if the two isoquant curves are intersecting each other, so they will be violating the property of transition. The marginal rate of technical substitution of labor for capital, as I said, that it is the amount of capital that is foregone for implying an additional amount of labor. Hence, it is the rate of change in the factor K in relation to 1 unit change in the factor L. This rate of change is diminishing. You can see there, if we a little bit enlarge this graph, you can see that labor is coming in additional by 1 unit, while on the other hand capital is being reduced first by 3 units, and then capital is being reduced by 1 unit. So by addition of one labor, the reduction of the capital is being further diminishes. So this diminishing behavior of marginal rate of technical substitution makes this curve convex. Isoquant map mean we can figure out different quantities of production, and the higher level of isoquant represent the higher level of output produced, and the lower level of isoquant represent the lower level of output produced. You can see that the lowest level of output produced at this isoquant representing points A and D. So A and D are on the lowest isoquant line, and it means that the lowest output is being produced of quantity 55, while B combination of labor and capital is presenting on the little bit higher isoquant curve, which is producing higher output level, that is 25, and the C and E combination of the two factors are existing on the highest level of output, which is producing 90 unit of output. So obviously a producer wants to maximize his production. If a producer were there, so he would have been gone for the highest level of output of 90 unit by choosing any combination of labor and capital which maximizes his production while keeping cost as at minimum. Another concept of return to scale in the production. Return to scale means that when we are employing or deploying the input variable or factor inputs, so the behavior of the production in response that depicts actually the return to scale. So there are three kind of return to scale: increasing return to scale, constant return to scale, and diminishing return to scale. Increasing return to scale means that when a certain proportionate change in the both of input capital and labor in our case leads to the more than a proportionate change in the output. It means that if you are using the same level of output by deploying less amount of the labor and capital, we can translate it into two ways. Either you are putting same level of increasing same level of same ratio of labor and capital, that is producing higher production than the previous quantity, that is also called an increasing return to scale. Or if you are putting if you are increasing the same ratio of labor and capital, but you are getting if you are increasing same level of output by deploying lesser amount of the labor and capital, so it is also called increasing return to scale, like that. Like here in the graph you can see that you are producing 100 amount of output at point P. Point P obviously showing you the some amount of labor and some amount of capital, but you can see that the production is being increased from 100 to 200. So 100 unit has been increased, so the amount of labor and amount of capital both have been increased. They gone up from point P to point Q, but similar rate of production is now increasing again from 200 to 300, but the lesser amount of more labor and more capital is being employed. You can see that the PQ distance or PQ arc is higher than the QR arc, so that QR arc is lesser rise in the quantity of inputs. So you are producing same level of output by putting or by employing lesser amount of labor and capital, so that is called increasing return to scale. And you can see that if we are producing more 300 to 400 output, so if you are producing more 100 output by employing more lesser input use, so that is called increasing return to scale. And constant return to scale, obviously it means that if you are if the change of output is proportional to the change in input, it exhibits the constant return to scale. For example, if the quantity of both input of capital and labor are doubled, the output is also doubled, then the return to scale is said to be constant. Like here you can see that if output is increasing by 100 to 200 or 300 and 400, but the amount of labor and capital is being increased by the same ratio, you can see that the distance between the PQ, QR and RS are remaining equal. So this is called constant return to scale. And diminishing return to scale, again we can translate it or explain it in two ways. One is like that if you are increasing your labor and capital in the same proportion, but your output is produced as the lesser proportion, so it is called diminishing return to scale. Or you are producing same level of output by employing more amount of labor and capital, so it is also called diminishing return to scale. And that is explained in this graph. You can see that if you are increasing output from 100 to 200, so a rise of 100 unit of output, it requires more labor and capital from P to Q. But if you are jumping up from 200 to 300, you are producing more 100 output, but now you are employing more labor and more capital than the previous one. So you can see that the distance between P and Q is now little, and Q and R is getting more. So it means that you are putting more labor and more capital for producing same level of output. And similarly, if more 100 output is being produced and the labor and capital is employed now again higher than the previous one, so it is called diminishing return to scale. So that's how we can classify return to scale in three kind of scale: increasing return to scale, decreasing return to scale, and constant return to scale. So that is actually so far somewhat theoretical background of the production. And from next lecture we will do some mathematical and graphical practice. Thank you very much.